Dynamics, you get the molecule to a local minimum. That is, in fact, the local minimum nature would find. And then you go on to the next excited state. If you use a plain vanilla optimization method, which is the first thing we try, you will converge to the wrong answer. The answer can be so wrong that the chemist can look at it and tell you you could not get to where you got with nature from where you began. So you must do the optimization with dynamics if you want to get the right answer. But you can't do this. Reality steps in. The molecules of interest, which are far more complex than the molecules in this presentation, have hundreds of atoms and hundreds of degrees of freedom, which are the torsion and bond angles. There is no way we can vary all of them. So we've got to pick some, and we've got to do optimization to resolve the rest internally. So now it gets strange. I cannot use Gaussian to drive dynamics because Gaussian is a very expensive code. And we have to run it a lot. So I've got to do something to reduce the workload that I feed to my quantum chemistry simulator. So I'm going to get my collaborators to tell me what the important variables are. And the great thing about this problem is my collaborators believe they know what the important variables are. So I can get some guidance into reducing the size of the model. So this exercise is model reduction. Okay. They need us because if after we're done, we find that one of the variables hasn't changed, they can remove that variable from their interesting list. Or if we tell them, directly or indirectly, that a variable they didn't believe mattered did matter, they can add it to the list. And the final product of our exercise had to do both of those things. So, let's talk about model reduction. I'm now going to take my degrees of freedom and split them into two flavors. The X variables are the design variables for the dynamics. The C variables are slave variables that the simulator is going to find for me. How's that going to work? You fix the design variables, and Gaussian can find the minimum energy where these variables are frozen and these vary. That calculation takes a while to do, but we can do that. As part of this exercise, Gaussian computes the energy landscapes for several different excited states. So once we've done the initial calculation, we have the calculation for the excited states in hand. That is the way this calculator works. However, Gaussian is going to have a lot of trouble computing the gradient of the reduced model. Gaussian can, at great expense and sometimes incorrectly, compute the gradient of the whole thing. But that's incredibly expensive. Computing the gradient of the reduced model with respect to the design variables would require that Gaussian compute the gradient of the slave variables with respect to the design variables, and Gaussian is not about to do that. And neither are we. So we've got to drive dynamics, but we don't have a gradient. Oh, the other little bit. This thing here is an internal optimization. The internal optimization